Let's go over activity 2, basically data validation and ensuring data integrity. So the data file that we're going to work with comes from a real company that sells products both online and on TV, and they keep track of a lot of information regarding all the transactions. So what we're going to do is to read in the retailer.csv data file and do some data integrity checks and fix any issues that we see crop up. So I'm checking to make sure that R is looking in the folder that the data file is in, and I'll go ahead and read in the data. All right, so the first question asks us to get some practice with the Luberdate package, because if we look at the very first column of the retailer data frame, we see that the first column has date information. Now, by default, R reads it in and treats it as a categorical variable. We have a factor with 217 unique levels here, and we want to treat it as a date. All right, so we need to make sure that we load up library Luberdate, and then our task is to identify what form the date information is in, because depending on what the form is, that is going to dictate the function that we use to convert it into a date object. So how do we do this? Well, we just simply look at the information that we have available to us and note the ordering of that information. So it looks like the first number in the date is going to be the year, followed by the month, yeah, let's start that over. This is the month, then the day, then the year. So the command that we're going to use is, as you might expect, M, D, and Y. Now, there's no hour, there's no minute, there's no second information, so we don't need to put any underscores like HMS for hours, minute, and second. We literally just look at the date and determine what information is given to us and in what order, and that's the function that we will use. So what we're going to be doing is we're going to be taking that date column here and basically putting the converted object back into that very column. So retailer date, left arrow, MDY, retailer $date is going to go ahead and convert that object for us. And so we see now that we are correctly having that object in a date format. And now Luberdate will extract any sort of interesting information like the weekday, day of the year, etc. that we might want. So what we want to do is to verify that every date in the dataset corresponds to a Monday. And we can do that by extracting the day of the week just with WDay. What do we want to be extracting the day of the week from? Well, the values in the retailer $date column. And because we want the actual day labels, like Monday, Tuesday, Wednesday, we're going to put in label equals true. So if I just run this command, it'll print out what all the days of the week are for all the rows in the data set. And we see that indeed it looks like they're all Mondays. There's a lot of options that we didn't see because it wouldn't print all that stuff to the screen. So we could always just look at a table of the values when that's done, and we see that, okay, really Monday is the only day that is represented in the data. And that's to be expected because this has been aggregated at the weekly level, and to them the sales week starts on Mondays here. All right, so the next task is to figure out the month that appears the most in the data. A little hint that it appears over 13,000 times. So we're going to do something very similar. Basically, let's look at a table of all the months that appear in the data set here. So we're going to extract the month just with the month command here, as you might expect. We're going to look at the retailer $date column, and we're going to add that label equals true so that it's actually printing out January, February instead of 1, 2, 3, etc. So we print this out and we see that it looks like July is the one that appears the most at a little over 13,000 times. All right, question number 2 wants us to look at the very last column in the data set, which is the product column here. So basically these are broad categories of items that this company sells, and we're going to look for some data integrity issues. There's 4 or 5 issues, so let's see if we can identify these. So because product is a categorical variable, a good place to start is just to look at the levels of that categorical variable. What unique values does it see? So are there going to be typos? Are there going to be levels that should be combined together because they have different spellings or capitalizations? Let's just look at the levels here. And we'll just read through them. So scanning through these levels, the first issue we see is that it looks like this level is just misspelled. Electronics instead of electronics here. We probably need to combine those into the same level. We see that fashion is misspelled here. There's no equivalent fashion D category that is correctly spelled, so we could either change this or leave it as is. It's not really going to complicate any future analysis, but it's nice to have stuff spelled correctly. We have a lowercase home a, and we have a home a with different capitalization. We want to combine those levels. And we have an other and an other category with different capitalizations as well. We should combine those. And then we have watch A and watches A that we should combine. So 4 or 5 levels depending on, or 4 or 5 issues depending on whether you want to correct the fashion typo here. So, all right, how can we go about fixing them? Well, we're going to directly modify the levels vector of this categorical variable. So how do we go about doing that? All right, well, the first part of the command's already there. This is the levels vector, and basically I want to be changing elements in it. So I know I'm going to use the left-hand arrow symbol because I'm going to be doing some definitions. But I'm not going to change every single level all at once here. I could do that. I could actually type out the 30 elements, the 30 names that I want each level to correspond to, but I'm going to do it a little differently here. I'm going to refer to specific elements of the levels vector to change one at a time here. All right, so first let's deal with the electronics issue here. Now just counting out the position of the levels vector that I want to change, I see that basically I want to take the 1, 2, 3, 4, 5th element of that levels vector and rename it to electronics B. But I don't actually want to hard code it like this, because if the data changes, if we were to add in, say, a new level, or if we were to modify the levels, the ordering of the levels from the levels vector here might actually change. So hard coding what position that I want to be changing is a kind of unsafe and scary thing to do because it could potentially mess up the data if the data were to change. So instead, I want to write a command that automatically extracts what position I want to be changing. So I'm actually going to go up to the line above this and figure out how I can get what position inside the levels vector corresponds to the level that I want to change. Well, the which command is good for identifying positions inside of a vector that meet a certain condition. So let's work on this which command. Basically what I want to know is which entry here, which element of the levels vector is equal to electronics B. That's the one I want to be changing. So, all right, the first thing that goes inside which is the vector that I'm going to be searching in. And my vector actually is the levels vector here. So I'm asking which of the levels is equal to electronics B. And in fact, a better way to do it, because you might typo it, is to literally just copy and paste it here. And let's just run this command to verify that it's giving the right answer for right now. Indeed, that's the 5th element that I see. So, all right, I'm going to just copy and paste this into the square brackets here so that when R runs this command, it dives in as deep as it can down into the command and then works its way out. It evaluates the which expression, it evaluates to 5. So we're basically taking the levels vector, looking at the 5th element, and now reassigning it with the left-hand arrow symbol to be electronics B. So if I run this command and then look at the levels vector that results from it, I see that there is no more electronics B. Now we just have electronics B. You'll notice that the ordering of the levels has changed now. Before, electronics B occurred before or after electronics A. Now it's actually before. That's because we're basically changing this element and making it equal to this element. So that's why it's a lot safer to actually use the which command inside of the square brackets, because we see the position inside the levels vector that things are will actually change if we start modifying that levels vector. All right, so for the other issues, well, we can just pretty much copy and paste this code here and just change the relevant bits. So let's go ahead and change this fashion D so that it's not actually misspelled here. So same code basically, look inside the levels vector, figure out which entry is equal to fashion D at this point, happens to be the 8th element. So take that 8th element of the levels vector and let's actually just have it be fashion D here. So I will run that, we can check it, and we see that it's been correctly updated. The next issue is that we had that lowercase home A. So which position inside the levels vector is home A right now, all in lowercase, and we're going to take that entry and reassign it to be capital home A. Another issue was we had 2 spellings of other. Now I'm going to take the one that's in all caps and change it because by convention, it looks like we have lowercase letters in positions except for the very first letter here. So I'm going to rename the other in all caps to just other. And then finally, that last issue here with the watches, I want to change watch A into watches A and run this command now. All right, so we can check the levels vector to make sure that all the issues have been fixed. I forgot to run that other command, so I can run that one now. And so we see that we have a pretty good looking set of levels here. So we've fixed the data integrity issues with that product column. We can get a summary of, how often do we see each one of these products just by running the summary. I do say that there's kind of an additional issue where some of these categories are really rare. So like watches B, C, and D only appear a handful of times in the data set. It may make more sense in this case to actually combine all the categories of the watches together into just one level. But we're not going to do that here. We've just simply fixed the data integrity issue. Now let's move on to question 3, which is looking at a different kind of integrity issue where we have a constraint on the different columns in the data frame. So we have a column for the effective orders from TV, the effective orders from online, and in theory, at least, these two columns should be add up to the values in effective orders. Now this may or may not be the case depending on if there's data integrity issues. So let's explore to see, all right, how often do we have these two values add up to the value in effective orders, and how much of a problem is data integrity. So what I'm going to do actually is just to define a vector called x, which is going to be the result of looking at the effective orders column and then subtracting off the sum of the orders from TV and the orders online. So what I'll do is I'll say retailer $ effective orders here. So basically extracting out the values from that column, and then I can just take the sum of the orders from TV and from online. And in theory, this should give a vector of just all zeros if there were no integrity issues. So basically the way this works is that, all right, each of these columns are basically vectors. If we do vector arithmetic, the operation is applied to each element of the vector in turn. So basically x is going to be a vector of the differences between the values that we find in the effective orders column and the sum of the values that we find in the effective orders TV and effective orders online on a row by row basis here. So we can define that, and then let's just look at a summary. Now, if there were no data integrity issues, every single value would be 0, the minimum, the maximum would also be 0 here. And we don't see that. We see that, okay, sometimes these two columns add up to more than the effective orders, and sometimes they actually add up to something a bit less. So we definitely see some sort of data integrity issues. So not every value is 0. So we do have a data integrity issue. So about what % of rows have issues with regard to this criteria? Well, let's look at the fraction of rows that are not equal to 0, or the fraction of entries in x that aren't equal to 0. So we can do length which x not equal to 0. That counts up how many non-zero elements that we have in the vector x. And then we can just divide by length of x to turn that into a fraction or a percentage. And it looks like about 25% of those values or rows in the data set have data integrity issues in accordance with this criteria here. So that's actually quite a bit, and that's somewhat troublesome there. There must have been some sort of data collection issue where problems occurred. And same sort of thing with net sales TV, net sales online, and net sales tote as well. So we can very quickly rerun this analysis, just changing the columns names around. We should have that the net sales tote is equal to the sum of the net sales online and net sales TV. But if we define our vector x, look at a summary of it, we find that actually none of the values are 0. So there are no rows where those two columns add up to the net sales total column here. So every value is non-zero. So no rows have their sales add up to what they should be. So that's an issue that you'd have to go back and actually ask these people, saying, hey, what's going on with these columns? Why don't we actually have these things adding up together. So what we find is that data integrity on these columns is compromised. About 25% of the rows do not have their effective orders from TV and online add up to the total effective orders, and all of the rows do not have their net sales from TV and online add up to the total. So we do have some pretty severe data integrity issues. All right, now number 4 just goes through and methodically asks us to look at every single one of these columns and to identify and fix any data integrity issues here. So let's go through fairly quickly what each of these columns have and what the issues are. We start out with price category, which is supposed to be a categorical variable with levels 10, 22, 34. That's some internal coding that I'm not exactly sure what those levels represent, but it should be a categorical variable. Right now, if we look at the class of object of price category, we find that R is currently storing them as integers. Same thing from over here. And so we need to make this a factor if we want it to be a categorical variable. So all we have to do is basically redefine the values in that column to be the original values, but forcing it to be a factor. And that converts it into a categorical variable. You'll see that that gets updated here. We now have price category being categorical. All right, number of products, well, that is a numeric variable. It should be bigger than 0 here. So let's go ahead and look at the summary of this column. We can go through and see, all right, what kind of values do we see in this column here? And we see it ranges from 1 up to 1525. So seems like a perfectly reasonable range of values for a weekly aggregate here. And we can ensure that they're integers here by looking at the class of this vector as well. So we see it is integer, so this column is okay. No issues there. They're all integers. They're all positive, about what we would expect. All right, showings, the total number of instances that the product group was featured. We can essentially use this same code here. We're just going to change the name of the column that we're looking at. So if we look at a summary of the showings, well, we have from 1 up to 5,515. That seems like a big number. We might have to go and actually check that with the data collection people and be like, hey, this seems like a lot of times to show a particular product group on TV, but who knows, maybe in some particular week it was, jewelry week, so they only showed jewelry on that television show there. So, all right, we can't really judge whether or not that's a valid value or not. We'll assume that it is. The only thing we have to make sure as well is that it's integer. So this column is okay as well. We have positive numbers. They're all integers. We're happy. Duration, the total number of seconds that the product was featured on TV. Well, another numerical variable. So we start out by looking at its summary. One thing that we know is that duration should be positive, and they shouldn't be longer than the length of the week itself here. So there's only so many seconds in a week. If we look at a summary of the showings, we see the smallest value is, we're looking at duration. Let me switch that up. We see that we do have a few zeros in here, and that doesn't make any sense because, the product had to have been shown on TV for it to show up in this data set, so we see zeros. They shouldn't be here. And the biggest value for seconds is this number. All right, is that too big to be realistic? Well, let's convert that into minutes and then convert that into hours. So that's about 9.35 hours of showtime over the course of the week. That's perfectly reasonable. That's not more than the number of seconds in a week, so we're happy about that. So what do we need to do? Well, we need to fix the issues here. We basically need to take all the values that are 0 and change them into NAs because whatever that value was, we just don't know what it is. So what we'll do is we'll use the which command to identify where inside the column, the duration column, we have zeros. If I just run this little bit, it says, we actually only have 2 zeros in the data frame here. I can confirm that there's zeros by looking at those particular positions, by turning on the square brackets and actually looking at the 17,850th values, etc. So those are the zeros, and I want to make them NAs. So I do left arrow and NA here. Now, there's no double quotes around here or anything because NA is a special object. R knows what NA means. We're not treating it as a word. We're treating it as just something that's missing. So we've taken care of that data integrity issue, and now we can move on to the number of viewers of that product group over the course of the week. So we know it's integer. It should be positive. So, all right, we go from 1 up to 5,515. Wrong column. Let's do that again. It goes from 401 up to 102,000. That looks pretty good. Are they all integers? Yes, they are. So no issues. Net revenue. All right, well, net revenue is numerical. So let's go ahead and look at the summary of it here. So we find, I think I'd fix this by now. We find that the minimum value is negative and the largest value is 703,000 here. Do these values make sense? Well, do negative values make sense in this case? Yes, it could be that products being sold were so deeply discounted that they actually lost money over the course of the week from selling them. And it could be that some products were very expensive and shown really quite often, so that you actually just did bring in a tremendous amount of money. There's nothing that automatically disqualifies any of these values as invalid. So, we're actually pretty happy here. It looks okay, because we can have negative. Gross margin, well, something very similar to net revenue here. It can be positive, it can be negative. Let's just take a look at these values and make sure they seem reasonable here. From minus 6,600 all the way up to 276,000 here. So it looks okay as well. No obvious data integrity issues in this column. Product discount. So we have a percentage written as a decimal. So we know these numbers should be between 0 and 1. Let's see if that's the case. We look at a summary. The smallest value is indeed 0, and the largest value is in 79%, so highly deeply discounted. So it's fine, all between 0 and 1. Well, what about the shipping discount? Same sort of restriction on the values that are allowed between 0 and 1. And we see the smallest is 0, the max is 1. So no integrity issues there. Number of orders, the number of orders for all products shown in that product group. All right, so we have an integer vector allegedly here. So we'll look to make sure that these values make sense and then confirm that they're integers. It goes from 0 for number of orders. That's fine. 0 is okay in this case because maybe just no one bought a particular product that was on TV, all the way up to 14,500. All right, that seems fairly reasonable. Are these all integers like they should be? Well, let's look at the class of that object. And it is, so we're happy. No issues here. Total sold, the total number of items sold. It can be higher than the number of orders if someone ordered more than one. Well, same sort of deal with number of orders here. We need to make sure that it's 0 or above and that we have integers. So looking at a summary, it goes from 0 up to 14,800. That's fine. It's numeric instead of integer here. So that's a little bit puzzling. Let's take a look at the values that we see in here. So this is numeric, not integer. And by looking at a table, oh, well, what's going on here? We see that a lot of these values are fractional. Now they're really close to 2, and if I scroll up here, really close to 1, but something looks like it happened when the data was being collected. Maybe some arithmetic operation made these numbers slightly less than an integer or slightly bigger. So we do have a few issues. So let's actually print out the first few values of the total sold. And in fact, there's a 7.9 right there. So we do have a pretty big issue here. These are not necessarily integers, so this is really quite odd. What do we do? Well, the best plan of action would be to go back and actually talk to the company and be like, hey, why are we finding non-integers sometimes in these values? But for the time being, well, let's give the data collection process the benefit of the doubt, and let's actually just round to the nearest integer. How can we do that? Well, let's redefine the values in the total sold column to be just what the values are rounded to the nearest integer. That's what round will do. So if we do that, this will fix that data integrity issue. think. Now let's look at a table of all the values in totes sold, and we're just seeing integers here. So yeah, it looks like we're happy about this. It's not the integer class because it started out as a just general numeric class. Rounding doesn't force it to be integers, but just by looking at the values in here and knowing what the round command does, they are all going to be integers. All right, cost of goods. Well, cost of goods we know has to be bigger than 0. It did cost something to acquire the product here. Might have been a very small value, but we know that it should be bigger than 0. So if we look at cost of goods, we find zeros in there. Some of these guys, wow, must have been really expensive products. Over the course of the week, the total cost of goods for that product group was over $460,000. But we'll have to just trust that number for now. All right, so it can't be 0, so we need to go and eliminate all those zeros, basically replace them with NAs. So how do we do that? Well, we take the column and then refer to those positions that contain zeros. So we turn on the square brackets and then put in the which command. Well, which of the values in that column are equal to 0? Let's set those equal to an NA. All right, so now when we get a summary of the cost of goods, it'll report the number of NAs, which is that 2674 here. All right, price, well, another numeric quantity. Bigger than 0, some things might have been sold for really cheap. Let's just take a look at the range of values. Anywhere from $10 up to $116,000, which is really big, the average price of all products sold in that product group. So, maybe they do have a product that actually sells for over $100,000. Maybe this is a particular type of car. There's an other category. So we don't actually know what this might correspond to. We might double check with the company to make sure that this large value is reasonable. But we'll have, for the time being, just assume that it is here. Looks okay, but a rather big value for the maximum. All right, markup. The average markup over all products sold in that product group must always be positive. Discounts applied to the product may make itself less than the cost of goods, though. So let's ensure that we all have positive numbers in here by looking at a summary. We don't. We see some negative numbers here. So something very similar to what we had done here for the cost of goods. We basically want to redefine certain elements of the markup column. Which ones do we want to redefine? Well, the ones which have values that are less than 0 here. So let's make all those NAs. So now if we look at a summary, it goes from 0 up to 100% basically. This might be a scaled version of what the markup is, but we have 237 NAs now. All right, net revenue TV. And you can start seeing why 80% of your time in any sort of data mining project is caught up with data processing here. This is fairly tedious. Net revenue from callers during the TV broadcast. All right, it can be negative, it can be positive. There's no issues here. There's no constraints on the actual values. And then net revenue online, well, same sort of thing. We're just looking to see if we have values that make sense. Here's something that's interesting. There's no products that had negative net revenue coming in from online. So TV, not so much. Online, all positive numbers. That's kind of interesting. Effective orders, well, the effective orders, taking into account returns, obviously the minimum value needs to be 0, and these should be integers, so let's take a look. Issue here. We have negative numbers, so let's go ahead and replace those negative numbers. So let's take the values in the effective orders column and then single out the ones that are less than 0. Take the ones which have values less than 0 and set them equal to NA. Let's look at a summary now, and it goes from 0 up to 12110. All right, well, what's the class of object here? Should be integer, and it is. All right, so we fixed that column. Same thing for the effective orders coming from TV. All right, so let's just look at a summary. We see negative values once again. So just a bit of copying and pasting, replacing those missing value or those values less than 0 with NAs, and now ensuring that's an integer. All right, well, the ones from online, you know the drill. Let's just see. I bet we have negative numbers here. We do. So let's get rid of those negative numbers. Extract the ones which have values less than 0, set them equal to NA. And they're still integers, so we're good. Finally, last 3 columns here. Finally getting to the end of here. Net sales total. Well, these can be negative, they can be positive here. So there's no constraints necessarily on these numbers. We see that it goes from minus 1,200 up to over 667,000. Seems reasonable. What about from TV? Well, you know, if the total column didn't have any issues, I betcha the TV column won't have any issues as well. Looks fine in here. And then finally, for online, I bet you this one will be fine as well. So let's look at a summary of the net sales online. Yeah, everything looks good. All right, so that's the data cleaning process. You literally just go through systematically every single one of these columns and make sure that all the numbers make sense from a logical point of view. Ones that don't, you can replace with missing values. And once you've done that, then you can start actually doing some sort of analytics. One thing that might still need to be done, however, is looking at transformations of the original values. Because very often we find histograms that are very strongly skewed toward larger values. That makes a lot of algorithms and techniques more difficult to apply. And so one way to fix that is with the logarithmic transform. So let's look at a particular column that has this issue here, the net sales total. And if we look at this, we have the right-handed skewness. So there's some outliers at really, really large values. And this is going to make analytics more difficult if we were to use this column here. So we'd like to, instead of using the original values, maybe come up with a transformation that makes this overall distribution more symmetric. And we know that taking the logarithm often can accomplish that feat. However, for this column, what we saw was we had negative numbers here. We can't take the log of 0. We can't take the log of a negative number. So a trick around that is to basically add just a constant to every single value so that they become positive. In this case, we could add 1282 to every number so that the smallest value would be 1, and then take the logarithm of that. That would make the distribution a bit more symmetric. Let's just see that in action here. Let's take the log base 10 of 1 plus the values inside that column. Not 1 plus, 1282 plus, that's what we were just talking about. And yeah, it looks a lot more symmetric here, a lot more easy to deal with. However, is that an okay thing to do? So it's okay to do as long as the number that we're adding isn't too big with respect to the range of numbers that exist in the column there. Now, let's go back and look at the summary of that column. What we see is that the median value right here is 1012. So half the values in this column are less than $1,000. Half the numbers are bigger than $1,000. Adding 1282 to each number more than doubles half the values in the data set. And that's a significant change. If we're adding a dollar to values that go from, say, 1 up to a million, where the average is a few thousand, adding 1 doesn't really change the values all that much. But in this case, yeah, adding this large number really does change the values. So we cannot get away with this trick in this case because adding 1282 substantially changes a large number of values. The median is 1012, so this would more than double over half of the values in the data set. All right, there we go, and that concludes activity 2.